Welcome one, welcome all. Over the next few weeks, we will discuss thermal physics and thermodynamics. Thermal physics is concerned with understanding the properties of macroscopic systems, which are themselves characterized by only a few state variables. Macroscopic state variables, as we shall come to see, relate to microscopic motions of atoms in the system, thus allowing us to infer atomic information from simple macroscopic measurements. Thermodynamics is a more general study of how macroscopic systems transform and use energy. We will further explore each of these topics over the coming weeks, but today, let's begin with a discussion of the first principles we will need to understand these topics. We begin by introducing the atomic view of matter. The idea that matter is made up of atoms is not actually a new one. It can be traced back as far as a thought exercise proposed by the Greek philosopher Democritus. Democritus was born circa 460 BC. His thought experiment can be described thusly. Imagine that you have a block of a substance, say cobalt. Imagine that you also have the world's most perfect knife, as sharp can be. You take your block of cobalt and your world's most perfect knife, and you cut the block in half. You now have two halves of your original block. You throw half away, and you have half a block remaining. You now take the knife and cut the half of a block in half, again discarding half of the cut so that you have a quarter of the original block. You repeat this process over and over again, and eventually Democritus hypothesized that you would have a remaining piece so small that it could not be further subdivided, even with the world's most perfect knife. At this point, you had an indivisible essence of your original block. Democritus called this the atomos, or indivisible. It is from this that we derive the word atom. Many of you probably know that an atom of cobalt is itself made of protons, neutrons, and electrons. However, in the spirit of Democritus's thought experiment, if you were to further subdivide this and split the number of protons in half, you would have a different atom entirely. And it would no longer be cobalt. But for a discussion of this, we'll wait till the end of the semester. We now turn to a quick discussion of common phases of matter. Your textbook notes that most materials can exist as a solid, a liquid, or a gas, and states that these are the most common phases of matter. I'd like to add the caveat here that this is probably true in your day-to-day lives. However, the most common phase of matter present in our universe is most likely a plasma, as this is the state that we find most of the matter in stars. With that said, a solid is a rigid macroscopic system of particles connected by spring-like molecular bonds. A liquid is a system of weakly bonded molecules. A gas is a system of molecules that move freely, interacting only occasionally during collisions with each other or with the container walls. We will speak of both liquids and gases as being fluids, though I recognize that this may not quite fall in line with the colloquial speak. We next turn to a very common measurement, that of temperature. In this course, we will use a pair of definitions for what we mean by temperature. The first definition is temperature is a measure of how warm or cold a system is with respect to a given standard. One such standard is produced by assigning a unique temperature-dependent response to being in thermal equilibrium with ice water at standard pressures. We could say that this is then 32 degrees Fahrenheit or 0 degrees Celsius. Likewise, when in thermal equilibrium with boiling water, we could define this response of our thermometer to be the condition of 212 degrees Fahrenheit or 100 degrees Celsius. You can read about this relation more in your textbook. The relationship between temperature measured in Fahrenheit and temperature measured in Celsius is provided here as the temperature in Fahrenheit is equal to 9/5 the temperature in Celsius plus 32 degrees. A second definition of temperature, which we will become quite familiar with, is that temperature is a measure of the average translational kinetic energy per particle of a given system of interest. We will turn to this definition over and over again throughout the semester. We now define state variables as parameters describing the macroscopic state of a given system. Some examples of state variables include volume, pressure, mass, mass density, and thermal energy. The mass density, as you've probably seen previously, can be described as the mass per unit volume. We also take this opportunity to describe thermal equilibrium. Thermal equilibrium requires that the system's state variables be constant and unchanging. For example, a gas is in thermal equilibrium if after a sufficient period of time, the pressure, the volume, and the temperature have reached steady state values and are unchanging. We will find these state variables to be incredibly powerful at allowing us to characterize the macroscopic state of our system. While we're defining quantities, let's also define number density, which is the number of particles per volume. It would have units of per volume, such as per cubic meter, per cubic centimeter, so on and so forth. Let's also define the atomic mass number. The atomic mass number is the sum of the number of protons and the number of neutrons for a given atom. A particular isotope is uniquely identified by the number of protons, which tells you which atom you're speaking of, and the number of protons plus the number of neutrons, which tells you specifically which isotope of that atom we are speaking of. A common shorthand for this would be to use the atomic symbol and superscript the atomic mass number. To ease finding this on the periodic table, I will sometimes subscript the number of protons so that you can easily place it on the periodic table. Let's also examine the atomic mass unit, U. The atomic mass unit, U, is defined as 1/12 the mass of the carbon-12 nucleus, such that the mass of carbon-12 is 12U. In kilograms, 1U is approximately 1.67 times 10 to the minus 27 kilograms. You have likely seen Avogadro's number in one of your prior classes. If not, 1 mole, or Avogadro's number of anything, is roughly 6.02 times 10 to the 23. If we wanted to know the number of moles of a substance, then it is the number of particles divided by Avogadro's number. The total number of particles is the mass divided by the mass per particle. Similarly, the number of moles can be found as the total mass divided by the molar mass, which is the mass of 1 mole of substance. As we shall see shortly, a rigid gas-filled sphere can be used as a thermometer in that the pressure will be related to the temperature. Again, we will see this shortly. If we carry this experiment out with different gases, we note an interesting occurrence, that a plot of pressure as a function of temperature is linear. Again, we will see why shortly. But another interesting facet is that if you plot the data for different gases, the trend lines all seem to meet at pressure equals 0 at a temperature of roughly minus 273 degrees Celsius. We then call this the absolute zero, and this allows us to produce an absolute temperature scale, the Kelvin scale. To convert Celsius measurements of temperature to Kelvin, we say that the temperature in Kelvin is the temperature in Celsius plus 273. So 0 degrees Celsius is approximately 273 Kelvin, and minus 273 degrees Celsius is approximately 0 Kelvin. The notion of absolute zero implies that there is no negative temperatures on the Kelvin scale. This will be useful for us for our second definition of temperature. Recall, our second definition of temperature is that temperature is a measure of the average translational kinetic energy per particle of a given system. Kelvin scale is thus useful in that it can be thought of as a direct relationship to the average translational kinetic energy per particle. Let's now briefly examine thermal expansion. The linear change in length as the temperature changes can be described as the change in length delta L divided by the length L is equal to alpha times the change in temperature delta T, where alpha is the coefficient of linear thermal expansion. Here we see an illustration of a rod of length L at some temperature T that then has its temperature increased to T plus delta T, and its length is correspondingly now L plus delta L. Materials often expand equally along each axis, but this is not a firm requirement. And so we could also write that delta volume over volume is equal to beta times delta T, where beta is the coefficient of volume thermal expansion. Let's now quickly explore phase changes. Let's use the common system of ice, water, and steam. Imagine that we begin with ice at, say, minus 20 degrees Celsius. As we add energy to it as heat, the initial response is that the temperature of the ice increases. The ice is warming. As more and more energy is added, the temperature will rise until the ice reaches 0 degrees Celsius at standard pressures. Then, any added energy does not go to raise the temperature of the ice. Instead, it goes to melt the ice and turn it into liquid water. And that is this horizontal plateau we see. Once the phase change from solid ice to liquid water is complete, then any added energy goes into warming the liquid. And this will continue until the liquid water is brought to a temperature of 100 degrees Celsius, at which point any added energy goes into converting the liquid water into steam. And that is this horizontal plateau. Once all of the liquid water has been converted to steam, then any added energy goes into increasing the temperature of the steam. I'll note that these two horizontal plateaus noted here, the lower one represents the melting or freezing point, and this upper one represents the boiling or condensation point. Here we see a pair of pressure temperature phase diagrams. To the left, one for water, to the right, one for carbon dioxide. For the water pressure temperature phase diagram, we see that at 1 atmosphere, or standard sea level pressure, as we increase the temperature, we begin at solid ice, and then when we get to 0 degrees Celsius, the solid and liquid are in phase equilibrium with one another along this solid line. But at 1 atmosphere, past 0 degrees Celsius, we have now moved into liquid water, continuing to increase the temperature up to 100 degrees Celsius. We see at 100 degrees Celsius, the liquid and the gas are in phase equilibrium with one another, and going through 100 degrees Celsius at 1 atmosphere, we turn into the steam phase. For carbon dioxide, we see that at 1 atmosphere, below minus 78 degrees Celsius, the carbon dioxide is in the solid form, and then above minus 78 degrees Celsius, we are in the gaseous carbon dioxide phase. This process of going directly from solid to gas is called sublimation. We'll spend a bit of time in our lecture discussion sessions going over reading and interpreting phase diagrams. Our model of ideal gases will consist of tiny hard spheres that occasionally collide with one another, but otherwise do not interact with each other. They may also collide with the walls of any container that they are in. The density of our ideal gas is considered to be low, and the volume occupied by the gas particles is small compared to the volume of the container. The temperature of our ideal gas is also taken to be well above that of the condensation point. The ideal gas also obeys a law relating 4 state variables called the ideal gas law. We have that the pressure times the volume is equal to the number of moles times the ideal gas constant R times the temperature. This can also be written as the pressure times the volume is equal to the number of particles times Boltzmann's constant times the temperature. Here we see a plot of P times V against N times T, and we see, for our ideal gas, a linear relationship where the slope is R, the ideal gas constant, 8.314 joules per mole Kelvin. If the gas is sealed in a container such that no particles or moles can escape, then PV equals nRT can be written as P later times V later divided by T later is equal to P earlier times V earlier divided by T earlier. In other words, the quantity pressure times volume divided by temperature is a constant for an ideal gas in a sealed container. A common tool that we will avail ourselves of is a PV diagram, where pressure is plotted on the vertical axis and volume is plotted on the horizontal axis. We will spend quite a bit of time looking at PV diagrams, but here I'd just like to point out that there are two different paths shown here that carry us from state 1 to state 3. This looping path and this path that stays at constant volume and then constant pressure. You can probably see that there are an infinite number of paths that carry us from state 1 to state 3. But some paths are easier to understand than others, and for this reason, they will be of significant use to us. We'll also spend a great deal of time talking about reversible processes and irreversible processes. I'll ask that you examine your textbook for this section, and we'll cover this material in our live lecture discussion sessions. Qualitatively speaking, as an example of a reversible quasi-static process, if the piston moves very, very slowly here, you are always in a state where you can undo the last step. In this case, if a membrane is broken, the process is quite sudden, and this is not reversible. This is an irreversible process. A few moments ago, we spoke of processes at constant volume and constant pressures. Here, we see a PV diagram representing a constant volume process carrying us from state 1 to state 2. You might imagine the rigid container we spoke of previously. As we increase the temperature within, we'll say that the volume is unchanged, but the pressure increases. We can see this from our ideal gas law, that if PV equals nRT, then P is equal to nR over V, that quantity, times T. If we hold the volume fixed, then N is a constant, R is a constant, V is a constant, P is proportional to T. In this lower figure, we have what's called an isobaric process, a process performed at constant pressure. So on our PV diagram, we have a horizontal line. In this case, returning to our ideal gas law, PV equals nRT, if the pressure is held fixed and N is held fixed, then we have that the volume is equal to the quantity nR over P, end quantity, times T. In this case, with a constant pressure, the volume is proportional to temperature. Finally, for today, we turn to our isothermal process, where the temperature is held fixed. Here you might imagine that the piston is within a thermal reservoir, holding the temperature constant. In this case, PV equals nRT, well, if N is held fixed and T is held fixed, then the entire right side of this equation is a constant value, such that P times V is a constant, and we have these characteristic curves, where P times V is a constant, or P is proportional to 1 over V, such that P is inversely proportional to V. Okay, that's all for today. As always, you are all awesome. Have wonderful days. Thank you for stopping by. Don't be strangers. Enjoy your days, but not so much that we don't see you next time.